Hey class, a few of you have been asking me about the last workshop problem, so I thought I'd go ahead and make you a video. In a lot of ways it's quite similar to the last problem we were doing in class that we didn't get all the way through yesterday on Wednesday. But yeah, I thought I'd give you guys some pointers on this one. So once again we have a three-step process where we go from A to B to C and then back to A. A to B, we're told, is occurring at constant volume, so we know VA equals VB. Alright, then B to C is a isothermal transition, so we can see our temperature at B and C are the same, and we're given that temperature. We're also given the temperature at A. And then we know that then we have an isobaric transition back, and so PC and PA will be the same as it moves back to its original starting position. And all we're asked for is one thing: what is the efficiency of the cycle? So we know efficiency can be written a few different ways. We know that it's equal to the work over QH, or substituting in for the work, we know that the work is QH minus QC over QH is the efficiency. So you can also write efficiency as 1 minus the magnitude of QC over the magnitude of QH. So you can really go about this problem multiple ways. I've solved it twice myself. Once finding the work in QH, and then I've also done it again finding QC in QH. I'm going to go ahead and point you guys in the direction of the second solution just because it's a little simpler, but either way is totally fine. It's almost the same amount of work no matter what you do. Alright, so to find the efficiency using this equation over here, we're going to need to know what QC is, the heat exiting, and QH, the heat entering. So from looking at the problem, we can observe that our QH, the heat coming in, is going to be a combination of the heat entering the system during transition AB plus the heat entering the system during transition BC. So I'm trying to color coordinate things here with our image. We also know that the QC is going to be heat that's exiting during our isobaric transition, and so that's going to be equal to QCA. Alright, so the question then is, what is our Q value during each of these different transitions? So QAB, we have a transition where we're having constant volume, and so we know from our handy equation sheet about thermodynamics, or just from our notes or our memory, that for a constant volume transition we know that the heat entering the system will be CV N delta T. And the nice thing here is we know what N is, we know what delta T is, so the question is, what is CV? Well, CV is going to be equal to, if we look up here, we have a diatomic gas. Our degrees of freedom are 5, since we're told it rotates but does not oscillate. So CV is just the degrees of freedom over 2. So we're going to have 5 halves N, or excuse me, R. 5 halves R is what our CV value is. 5 halves R N delta T. So straight away we know R, 8.31, N is our number of moles, which is given to us, and delta T we also know, since it's going from 120 to 370 K. You can calculate and quantify QAB. Cool. Sounds good. What about the Q during our isothermal transition? So QBC, for that we have to look at what happens during an isothermal transition. So we're told that the Q, the heat entering our system during an isothermal transition, which is weird, right? We're adding heat, but the temperature's not changing. Okay, so Q is going to be directly related to the work. Since there's no temperature change, all of your heat added will result in work being done on the system. So Q is equal to our work, and our work we know is equal to nRT times the natural log of your final volume, which in this case would be the volume at point C, over your initial volume, the volume at point B. Cool. So if we can find the volumes, we could find what QBC is. Sounds good. I'm going to come back to that here in just a second. And then lastly, over here, QC, which is just QCA, is an isobaric transition, which we know is going to be equal to CP and delta T. And we know CP, since we have 5 degrees of freedom, is going to be 7/2 R, and then N delta T. Once again, we know N and delta T, so we can solve. So determining QAB and QCA should be relatively straightforward. The question then really comes down to is how do we determine QBC? Because we're not given the volumes. We make some observations up here. If I scroll up a little bit, we have some observations up here that we do know that our pressure at A is equal to our pressure at C, our volume at A and B are the same, but that doesn't necessarily help us solve directly. So let's think about what we have going on here. So we don't know the volumes, all we know is the temperature and a number of moles. Alright, so let's consider our volume. So volume, using PV equals nRT, right? We know that the volume at point C would be equal to nR temperature at point C over the pressure at point C. And similarly, the volume at point B would be equal to nR temperature at point B over the pressure at point B. So the problem with that, though, is that we don't know really anything about our pressures, right? We have PC and PB here, so those aren't super helpful, all right? But one observation that we can make is, let's ignore this equation since we don't know anything about PB, and instead, if we look up at what we told ourselves earlier, look, our volume at A and B are the same. So what we can do is we can come down here and say, well, that wasn't helpful. We do know that VB equals VA, and so using the same ideal gas law, we can say that VA is nRTA over PA. Okay, well, we still don't know the pressure at A, but we do know that the pressure at A and C are the same. Again, we made a note of that up here because we have constant pressure transition. So what we can do then is, if we're trying to determine VC over VB up here, what we can see is that VC over VB, that's a B, is equal to VC, which is nRTC over PC, divided by VA, which is equal to VB, so that's nRTA over PA, and what we can see, we got N and R can cancel out, and we know that our PA and PC can cancel out, and so what we can find is that VC divided by VB is just equal to TC over TA. So what we can do then is we can rewrite QBC. So if you recall, we had a moment ago, QBC is equal to nRT. You can call it TB or TC, either way, it's the same temperature, multiplied by the natural log of VC over VB, and so that can be rewritten as nRTC natural log of TC over TA. So now that enables us to quantify QBC. So again, we can find our efficiency because we know it's going to be equal to 1 minus QC over QH, and we now know that QH is going to be QAB plus QBC. So we could really rewrite this as 1 minus the magnitude of QCA divided by the magnitude of QAB plus QBC. Alright, so I'm going to stop there and let you guys go ahead and finish the problem. If you have any additional questions, feel free to let me know. Have a box-worthy long weekend, and make sure you come back with some good physics stories.